Welcome to the ChemDoctor. What I'd like to do in this presentation is describe to the viewer what an isoelectronic series is and how to rank an isoelectronic series in terms of the size of the atoms and the ions. So the first order of business is to define an isoelectronic series. All right, so isoelectronic series, right? This is a collection of ions or atoms that all have the same number of electrons. All right, so let me get that down in words. It is a collection of ions or atoms that all have the same number of electrons. Okay, now there's a couple of things here. Remember that an ion is an atom that has an imbalance of electrons by comparison to the protons. And that can work in two different ways. You can have fewer electrons in an atom than you do the protons, and in that case you're going to have an ion that's positively charged, or on the other hand you can have more electrons in an atom than you do protons, and in that case it's going to be a negatively charged ion. And when we talk about an atom in general, or a neutral atom, this is going to be an atom that has the same number of electrons as protons. All right, so let's look at a simple series, and what we're going to do is focus on oxide, on fluoride. We're going to throw neon in, which is our neutral atom here, and then we'll have sodium ion and magnesium ion. So you see that we've got a total of 5 different particles here. We've got 2 anions, we have 2 cations, and we have neon. You'll notice that the anions and the cations bridge across a noble gas, all right, which is quite common for an isoelectronic series that might appear on a test or an exam in a high school chemistry class or university level general chemistry. So the first order of business is I want to take you through and show you that each of these 5 particles have the same number of electrons, and justify the charge or lack of charge on the particles. And then we'll talk about the rationale to rank these relative to their size, all right? From small to large, or from large to small, whichever I choose to do once we get to that point. All right, so first off, let's go through and identify the atomic number of each one of these elements. So for the oxygen, its atomic number is 8, fluorine is 9, neon is 10, sodium is 11, and magnesium is 12. All right, and now let's go through and look at the number of protons and electrons for each one of these ions. So in the case of oxygen, all right, the atomic number tells you the number of protons. So oxygen has 8 total protons that I'll show this way. Remember that each proton has a positive charge on it. Now, the fact that this ion has a net charge of -2 means that it has to have more electrons than it does protons. And since its nuclear charge is +8, in order for this to be -2, there needs to be a total of 10 electrons. So let me change the color on that. We're going to have -10 electrons. And when you do the algebra on this, you see that -10 plus 8 is equal to -2. And that is, of course, the charge on this ion. All right, and we can do the same little analysis for each of the rest of these. So for fluorine, we've got a total of 9 positive charges in the nucleus. it has a net charge, the ion does, of -1. The only way that we could get to that is if we had a total of 10 electrons in this particular ion. When we take the difference here, we get -1, and that's the charge on this particular ion. And remember that we call these anions. All right, now in the case of neon, we've got plus 10 protons, and we have minus 10 electrons. The sum total is 0. That's why this is neutral. And I think I'm going to go ahead and put this in words for anyone out there who's sort of weak in this area. All right, so this is a neutral atom. Now let's take the cations. Right, these guys are positively charged, so they're called cations. All right, and in the case of sodium, it has a total of plus 11 protons. Okay, and it also has 10 electrons. When we take the difference, you see the charge is plus 1. That's where this net charge comes from. And then finally on magnesium, we have plus 12 protons. And we also have minus 10 electrons. When you take the difference, you see that that's where the charge of plus 2 comes from, because we've got 2 extra protonic charges by comparison to the number of electrons. So each one of these guys has the same number of electrons, and that is the central requirement for an isoelectronic series. Now, what teachers and professors like to do is to ask you to relate the size difference of all of these atoms together. Now, to figure that out, there's 2 things I want you to think about. The first is, remember that what defines the radius of an atom or an ion will be the valence electrons and how hard they're being pulled on by the nuclear charge within the nucleus of the atom. So this is electrostatic force, all right, or Coulomb's law. And Coulomb's law, basically, you can look at Coulomb's law the following way. You can say, okay, Coulomb's law basically is the nuclear charge divided by the distance squared. And the distance that we're talking about is the distance between the nuclear charge and essentially the valence electrons. So let's very quickly take a look at what the valence is for each one of these atoms. And to do that, we're going to write the electronic configuration for each one of these atoms. All right. So for oxygen, for O-2 actually has total of 10 electrons. Its electron configuration will be 1s2, 2s2, 2p6. And I'm going to go ahead and underline the valence. Here's the valence. For fluoride, all right, its configuration is 1s2, 2s2, and also 2p6. Now, if the viewer's weak in this area, let's just do a quick count. You see, for either one of these, if we add the 6 to 2, that's 8, and then to 2 is 10. So both of these atoms have the correct number of electrons, and you can see the striking thing that's happening here is that each one of these atoms or ions has exactly the same electronic configuration. So they all are 1s2, 2s2, 2p6. They all share the same electronic configuration as neon. All right, let's get magnesium done here. So it's also 1s2, 2s2, 2p6. All right, so they all have the same exact electronic configuration. All right, now let's take a look at the nuclear charge. All right, in the case of oxygen, it's plus 8. In the case of fluorine, it's plus 9. In the case of neon, it's plus 10. In the case of sodium, it's plus 11. And in the case of magnesium, it's plus 12. So as we go left to right from the beginning of my electronic series here, my isoelectronic series to magnesium, you can see that the nuclear charge is increasing. So if I go back to this idea of Coulomb's law, which I'm going to abbreviate the following way and simplify, I'm going to say that really you can look at this this law as relative to this example, where we're taking a ratio of the nuclear charge to the distance squared. Now, you can see clearly, and this F right here, just to clarify this is the force of attraction that's operating on the valence electrons. And why am I emphasizing the valence electrons? Is because that's essentially where the surface of the atom is, all right? So this force of attraction, as we go from O-2 to magnesium +2, you can see that the force of attraction, or the nuclear, the top of this fraction, all right, is increasing as we go from O-2 to magnesium +2. And the distance in which the electrons are away from the nucleus is remaining the same, because look at the electron configurations here. The outer valence of each one of these ions, and in the case of neon, the neutral atom, and then for both sodium and magnesium, these outer electrons are all in the same energy level. They're all the same distance away from where the nucleus is. So the force of attraction is going up as we go across this isoelectronic series. Let me put this in words. Force of attraction. And it's increasing as we go left to right from O-2 to magnesium +2. So therefore, we can rank the size the following way. Magnesium ion is going to be the smallest one, because its force of attraction operating on those outer electrons is going to be the highest. Next in line is going to be sodium. Next in line will be the neon. Right? Next in line, and the second largest is going to be the fluoride. And the largest of all is going to be the O-2. All right? So O-2 is going to be the biggest one here in terms of the ions. And the magnesium ion is going to be the smallest. We figured that out by relating the nuclear charge and identifying where those valence electrons are, which happen to all be in the same energy level. So there's a net constriction as we go from O-2 to magnesium +2, because the nuclear charge is increasing, but the distance is remaining constant. So the force of attraction is going up as we compare O-2 to magnesium +2. So magnesium is the smallest, and O-2 is the biggest. And I'm going to go ahead and close the video now. I'd like to thank the viewer for taking the time to watch this, and hope you come back to my channel and my website. Remember, my website is www.chemdoctor.org.